Now that we understand what a vector actually is, we want to define some basic operations. Our first operation is going to be scaling. So we'll define it, then we'll do some examples so that we understand what's actually happening. Given a vector, v, whose coordinates are v1, v2, down to vm, so it's an m-dimensional vector, and a real number, a, av is the vector obtained by scaling v by a, whose coordinates are av1, av2, etc., down to avm. That is, when we scale a vector by a real number, which we'll often call a scalar, we obtain a new vector whose coordinates have all been multiplied by that number a. To understand this operation geometrically, let's start by thinking about scaling in one dimension, then extend to higher dimensions. So vectors in one dimension are pretty simple. They are simply a 1-by-1 matrix with a single entry. We can encode the direction of a vector by the unit vector u, which is the single entry 1, which points to the right by 1 unit, and minus u, which points 1 unit in the left direction. Again, they're called unit vectors because they have unit length, which is just 1. This allows us to think of the vector v as being obtained by scaling the unit vector u by a. So for example, if a is a positive number, then we have the following picture. If a is bigger than 1, then we can stretch the unit vector u by a factor of a to get v. This is the scaling operation. And if a is smaller than 1, we could think about compressing the unit vector u by a factor of a to get v. If, on the other hand, a is less than 0, then we have the following picture. So we can think about taking the unit vector u and rotating it 180 degrees so that the new vector points from the origin to -1. Then, as before, if a is larger than 1 in magnitude, then we can think about stretching the vector negative u by a factor of a to get v. Or if a is smaller than 1 in absolute value, we can think about compressing the vector minus u by a factor of a to get v. So from this perspective, we can very easily understand how scaling works in R1. We can break it down into 3 pieces. If we scale a vector v by -1, then this operation reverses the direction of the arrow. If we scale by a number a, which is larger than 1, then we simply stretch the vector v by a factor of a. Scaling by 1 over a compresses the arrow by a factor of a. So now we want to try to use our understanding of scaling vectors in 1 dimension to understand scaling vectors in 2 dimensions. So although the object may seem more complicated, it turns out that a 2-dimensional vector with entries x and y in R2 carries exactly the same data as a vector in R1, a magnitude and a direction, and we'll find that the scaling operation behaves the exact same way on the arrows. Again, we'll regard the vector as an arrow originating from the point 0, 0, or the origin, to the point x, y. And we can construct a right triangle. Since we know that the base of our triangle is x units, the height of our triangle is y units, the magnitude of our vector v must, by the Pythagorean theorem, be the square root of x squared plus y squared, which we write as r. The reason we use r is because if we square both sides of this equation, then we can think about this thing as a triangle inscribed in a circle of radius r centered around the origin. Then we can think of the point where the vector v intersects the unit circle as our unit vector. And we can think about v as being obtained by scaling this unit vector u by a factor of r. In analogy with the example in one dimension, these unit vectors provide our direction, and we can obtain any other vector by scaling one of those unit vectors. And if we want to find which unit vector points in the direction of any vector that we like, all we have to do is scale our original vector by 1 divided by its magnitude, so here's an example. The vector v, which has its x-coordinate is 3, y-coordinate is 4, that point lies on a circle of radius 5. If we want to find the unit vector, which lies in the direction of v, all we have to do is take our vector v and scale it by a fifth. And we can see explicitly that this is indeed a unit vector by the computation. So the moral of the story here is, just like in R1, scaling in R2 scales the arrow by either stretching or compressing, depending on whether your scalar, your real number, is bigger or smaller than 1. And if it is negative, then it also reverses the direction of your arrow. Now the move from R2 to R3 is relatively easy. So to understand the length of a vector in R3, we just need to use the right triangle below. So for any vector that points from the origin to x, y, z, we can start out by dropping a vertical line starting from the point x, y, z down to the point in the plane x, y, 0. Next, we connect the point x, y, 0 to the origin 0, 0, 0. This will form a right triangle, which from the side will look like. So to understand the length of our vector v, we just need to know the length of the two sides of the triangle, and just as before, we can use the Pythagorean theorem. For the dotted red line, which was a vertical line going from xyz down to the xy plane at xy 0, that line we know must have length z. And since we've already talked about how we can think about the xy plane as being sort of the same as R2, the length of the dotted blue line, that is going to be the square root of the x-coordinate squared plus the y-coordinate squared. So the length of our vector, which again we call r, is given by squaring the two sides, adding them together, and taking the square root. So instead of pointing towards a circle of radius r, our vector in R3 points to the sphere of radius r, which is the three-dimensional analog of a circle. Our unit vectors, which specify our directions, are not given by vectors that point to a unit circle, but by vectors that point to a unit sphere. And once again, the scaling operation behaves just the same as in the previous two cases. So here's an example. This vector points to the sphere of radius 6. If we want to find the unit vector in the direction of v, then all we have to do is scale v by 1/6. And again, we can verify this does indeed point towards the unit sphere by the computation. So while we can't visualize m-dimensional space for m bigger than 3, we make the general definitions that match our intuition in dimensions we can visualize. We define the distance from the origin to a point x1, x2, down to xm to be r, which is the square root of the sum of the squares of its coordinates. And in a seemingly strange turn of events, we declare the set of points satisfying the equation r equals 1, which is equivalent to saying that 1 is equal to the sum of the squares of its coordinates to be the unit m-1 sphere. So with this in mind, an m-dimensional vector points from the origin to the m-1 sphere of radius equal to its magnitude. And the operation of scaling by a real number behaves just as it does in lower dimensions. Multiplying by -1 flips by 180 degrees. Multiplying by a number a, which is bigger than 1, stretches by a factor of a. And multiplying by the number 1 over a compresses by a factor of a.